Hi, in chapters 3 and 4 we cover atmospheric energy and global temperatures. You can see the depth of the atmosphere is a barrier to the solar energy, and we did talk about how oblique angles near the poles are going to create less or more diffuse energy than more direct radiation that are going to occur at the equator year-round. And you can see noontime during high latitude winter, and I think I showed an example of that in Iceland, where I was. The atmosphere, basically, it's the air. It's a mixture of gases that are naturally odorless, colorless, tasteless, formless. Basically acts as a filter, removing much of the harmful components of the solar radiation before it reaches the Earth's surface, and it exerts a pressure of about 14.7 pounds per square inch at sea level, with most of it concentrated below 18,000 feet of elevation. The principal gases are nitrogen, oxygen, carbon dioxide, and argon. And you can see, just because of gravity itself and whatnot, air density decreases as we increase in altitude. So denser air is closer to the surface of the Earth than less dense air. You can see the composition of it here. You can see more than 3/4 of it is nitrogen, a little more than 21% oxygen. And you can see the relationship with temperature as we go up into the atmosphere. Okay, and this is with pressure in millibars. Temperature will be slightly different. You can see temperature generally goes down, but it does go back up a little bit as we get above the go into the ozone layer, which is O3. As we get further into the stratosphere. So we have the troposphere, stratosphere, and we get further and further out to the exosphere, about 300 miles up. In the troposphere, we have lapse rate. Temperature decreases as the altitude increases. This is in the troposphere. I did a neat experiment with that where I strapped a sensor to a drone and just flew up and kept track of the temperature, and that lapse rate definitely worked. It was pretty neat to measure this, and I brought this into some programs and measured this, but I only went up about 400 feet or so. But we can prove this. In the stratosphere, we have this inverted lapse rate, which basically means the temperature increases as the altitude increases, and that's because of the presence of ozone. And then we have the mesosphere and the thermosphere as we go further up. But regardless, as you go further up, temperature is generally going to decrease. Even in the stratosphere, it's not going to be very high. We have a tropopause, which is the boundary between the troposphere and the stratosphere. And you can see this lapse rate. So you can look at the temperatures that we're getting to here before we get into the stratosphere, where the ozone does exist. And we've got this lapse rate. Actually, when I did it, I found the lapse rates to be about twice that. I think it was about 3 degrees for about 400 feet in elevation, which I thought was kind of interesting. In function of the atmosphere, the ozonosphere absorbs UV wavelengths. So if we do not have ozone, some of these UV wavelengths get through and cause harm to people. Energy transportation, and then water transportation. So these are just some of the functions in terms of, we have gamma rays that are absorbed in the ionosphere, UV in the ozonosphere. Visible light gets down to the surface of the Earth. So you can see these different places where some of these different wavelengths, some of which are harmful to human beings, can get to. But typically most harmful radiation is filtered out above the tropopause. We have aerosols, which are suspended particles such as dust, and then we have gases. We have natural sources of some of these aerosols, like volcanoes, forest fires, plants, farming or whatnot, and then we have anthropogenic sources, incomplete combustion fuel, agriculture, road construction. So we have different causes of these aerosols in the atmosphere that can block out the sun as well as do some other things with this insulation. And you can see an example of this here. I think this was from a volcano. And then you can see, orange sunsets, industrial plumes, burning of farm fields or whatever. These days we hear the term, global climate change, global warming or whatnot. And there's a lot of debate about that, but we definitely do know that temperatures are changing. I think I'm going to have later in this class when we talk about glaciers. Glaciers are, melting or whatnot, but I've been to Alaska and there's some places where they're actually increasing in size. So we use this term global climate change, a more general term of global climate change, to talk about how some places are increasing in temperature, most places are increasing in temperature, some are actually decreasing in temperature, and the dynamics attached to some of these anthropogenic sources that we're inserting into these natural systems that didn't experience this. Other factors influencing air pollution, winds, and then local topography. So topography can act as a barrier, redirect movement, landscapes that can act as dust traps, and temperature inversion. It means what it says. So a layer of warm air over a city can trap air pollutants. We have an example there, mountains forcing air and moisture aloft, forming clouds, and eventually precipitation, which is called orographic precipitation. And then winds picking up and transporting dust particles. And you can see examples of forest fires. In 2018, there were a number of forest fires in the western part of the United States. But you can see how these affect the aerosol, air pollution in other places. You can see the inversion layer, what happens with this temperature, and how it deviates from these lapse rates and changes the dynamics of your local temperatures. And then the formation of smog, basically smoke and fog. And you can see an example here. Over a number of years, we've had ozone, so the depletion of the ozone layer. This was a concern when I was growing up in the 80s and 90s, not as much now. But you can see near the poles, for some reason or another, that we have much less ozone. So people who live near the poles, in the northern hemisphere, not too much of a problem, but in the southern hemisphere, places like South Africa, Australia, New Zealand, where those countries have higher rates of skin cancer because of this. And you can see just the energy balance. And we talked about this before, all of the different things that can happen to incoming insulation in the atmosphere or at the ground. We have refraction and reflection. We have a measure called albedo, and that's the measure of reflectivity off of a surface. So it's typically given as a percentage. So the Earth's average annual albedo is 0.31 or 31%. So there are some things that we can do. If we cover up, grass or snow or forest with asphalt, well, we're going to be changing the dynamics of the albedo. Okay? By nature, asphalt has a relatively low albedo reflectivity, so it's going to absorb a lot more energy. So if we go and just don't do anything with the actual topography itself, but if we replace low albedo materials with high albedo materials or high albedo environments, we're going to change the temperature of a particular location. And those are some of the things we need to be cognizant of. We have scattering. This, in general, you hear the term, this is what makes the sun blue, scattering, because it's scattered through components of the atmosphere in a wavelength that's blue. It looks blue to our eyes. And then the average temperature temperature ranges are dependent upon the amount of insolation as well as other factors. Places near oceans and large bodies of water are going to have less temperature range than places like, say Minneapolis or Bismarck, which can get really high. In the summer of 2018, they got really high over hundreds, but they will get into the negatives, 20s and 30s come wintertime.